Okay, today we've got another back to basics topic on the diff amp, or differential amplifier, also known as a long-tailed pair or diff pair or emitter coupled pair. We'll talk about the basic characteristics. I'm going to avoid getting into all the math and things like that, but just kind of show the practical details of how this circuit operates and how it's used. We'll talk about its small signal behavior and its large signal behavior, as well as how current sources can be employed to help the performance of this circuit. Now, the diff pair is really a fundamental building block for many analog circuits, especially things like op amps and multipliers and things like that. And this is the basic configuration of a discrete diff pair. A pair of transistors, typically that are matched, emitters coupled together, a load in each of the collectors, and then a bias current or operating current, also known as the tail current, being pulled down through the emitters. Typically called a long tail because ideally you'd have a lot of voltage across this emitter resistor so that any change in common mode voltage of the inputs won't cause a large change in the tail current. But we'll talk about that in a little bit. So the real basic characteristics or basic operation of a diff pair can be thought of a couple of ways. Let's consider the case when the input voltages are equal. Okay, when the input voltages are equal and these transistors are matched, the tail current splits equally between the two transistors. So we've got an equal emitter current, thus an equal collector current, and therefore the voltage drop across each of the loads is equal as well. So that the voltages here at the two collectors are also going to be equal. Another way to think about that is that if the input voltage difference is equal to 0, the output voltage difference is also equal to 0. And it's when these input voltages start to change is when things start happening in the circuit. Now we can talk about the behavior of this circuit a number of different ways. We'll take a look at it graphically. I've got a little mechanical simulator that I'll show you, and we'll make some measurements on the bench. So let's first discuss things graphically. This graph here represents the transfer characteristics of this diff amp. Think of this axis here as the input voltage difference, Vin1 minus Vin2. So when Vin1 is equal to Vin2, then that's when this difference is 0. That represents right here in the center of the graph. And at that point, that's where the tail current splits equally between the two transistors. The voltage drop at Vout1 and Vout2 is going to be the same. So that's why these two curves cross each other. Now if Vin1 minus Vin2 starts to go positive, this voltage is higher than this voltage, more of this tail current is going to go into Q1, therefore less into Q2, right? Because the sum of the currents in this node have to be equal to 0. So therefore we'll get more of a voltage drop here, so Vout1 will drop and Vout2 will rise. And we can see this behavior kind of happens, and once you get to a little bit more than 100 millivolts in one direction or the other, nearly all of that tail current is going into one side and not in the other anymore. And that's the basic transfer characteristics of a diff amp. Here's my little mechanical simulator to kind of show you what's going on. So here's my diff amp, Q1, Q2, the two load resistors, the tail current here. And let's imagine that the vertical axis of this piece of paper represents volts. Okay, where I'm at 0 volts down here and at 9 volts up here at the top. So you can kind of almost think of the elevation of where these little pointers are pointing as the voltage at each of those nodes. Okay, so if VB1 is equal to VB2, they're both at the same voltage level, the collector voltages are at the same level. But if VB1 goes up, okay, then more of the current goes into Q1, dropping more voltage across R1, and this voltage drops. Less current is going into Q2, so we have a less of an IR drop across R2 and its voltage goes up. And you can see that the circuit has gain. A small change in VB1 versus VB2 can mean a large change in the difference between Vout1 and Vout2. And the same holds true going in the other direction. Now in many applications, the input signal may be single-ended or differential, and the output may be taken from one side or the other or as a differential signal. So you can kind of use this as a single-ended amplifier or a single-ended to differential amplifier or a differential input to single-ended output. It all is a matter of what you choose to use as your input voltage and your output voltage. Alright, so let's make some measurements on the bench. This is the test circuit that I've got built up here on the breadboard. A couple of transistors. These are 2N2222As. Any general purpose transistor will work. And ideally they'd be from the same batch to be reasonably well matched. It's kind of tough to match them perfectly with discrete devices, but I got as close as I could get. I've got a pair of 10K resistors as our collector load resistors, and I'm using a 4.7K resistor as our tail resistor to create the tail current. And I've got set up a 9-volt power supply to bias the whole circuit up. I've got another variable power supply that's feeding both bases, okay, through 3.9K ohm resistors. And then I've also got this 33K resistor hooked up to another variable supply that I can use to vary this voltage with respect to that one. Right now I've got that disconnected. It's not in the circuit right now. So all we have is that part of this circuit to kind of show what's going on. Okay, we've got 4 multimeters here. This meter here is reading the input voltage difference, measuring essentially the voltage from here to here. Okay, and then ideally that's going to be close to 0 volts. I could see it showing just at a 2 millivolt or negative 2 millivolt difference right now. This meter is reading the voltage difference between the two collectors, VC1 minus VC2, or V out 1 minus V out 2 from the previous circuit. Okay, we can see that's, it's only about 124 millivolts right now. So a 2 millivolt input difference, 120 some odd millivolt output. This voltage here is measuring my common mode voltage here. Okay, so that's sitting at 3 volts. And then this last meter over here is reading the voltage at the collector of Q1 to kind of give us an idea, in this case, where the common mode voltage is, because these two voltages are almost the same. Now, this circuit can have quite a bit of gain. The differential gain of a simple diff-pair is basically the same as the single-ended gain of a non-degenerated common emitter amplifier, GMRC. So we can see this 2 millivolt difference at the input is creating a 120 millivolt difference here. That's not all due to gain. Some of that is just due to the imperfect matching of the two transistors. And it's very interesting to kind of look at how sensitive that might be. You may know that the base emitter voltage of a transistor will change about 2 millivolts for every degree centigrade change that you have. And if I put my finger on one of the transistors, you can actually see the difference voltage at the output changing. I'm making one transistor hotter. Let me take my finger back off of that. We can see that voltage coming back down. If I put my finger on top of the other transistor, we can see that voltage coming back down and now going negative the other way. So we can see that there's a lot of gain here. A small mismatch in VBE can cause a large change in the differential output. On an integrated circuit, this typically doesn't matter because the transistors are very closely matched thermally and in performance and everything else, so it's really not an issue. And of course, when building diff amps like this in discrete circuits, oftentimes you're employing feedback, sometimes in the form of emitter degeneration or elsewhere, that these mismatch issues don't become an issue. So let's apply our input voltage to one side here to start changing VB1 with respect to VB2 and see how that changes the output voltage. I'll connect up that variable power supply to the input here. And we can see that where I've got the supply set up, I've got about an 8 millivolt input difference here now, and I can see I've got an 800, almost 900 millivolt negative difference at VC1 minus VC2. If I reach up and adjust the power supply here to adjust the input voltage difference here, see if I go up to 60 or 70 millivolts, 60 millivolts here, I've got a 4 volt difference now between those two. If I go the other way and make, say, a negative 50 or 60 millivolt difference at the input, okay, and now I can see that I've got about a 4 volt change but in the other direction. So we can see we're kind of tracing out those transfer curves that I showed you earlier by moving that voltage back and forth. I've disconnected our input voltage here for the moment again to talk about one of the imperfect behaviors of this circuit. and that is that the output voltage, not only the common mode output voltage, but the gain is going to be a function of the input common mode. And here's why. If that common mode voltage is adjusted up or down, that changes the bias on the tail resistor and therefore changes the tail current. If the tail current changes, then the current going through the two transistors changes. That changes the transconductance and therefore changes the gain. So let's take a look at that a couple of ways. So without the input voltage turned on, let's just take a look at how the collector voltage, in this case VC1, varies if I vary the common mode. So right now the common mode voltage is sitting just about 3 volts. If I turn that down, we can see the voltage at the collector going up, right? Because as this voltage is coming down, the tail current's going down, so the voltage drop across RC1 is changing. So we can see that there's some common mode gain, if you will. The common mode output is going to be a function of the common mode voltage at the input. And for a differential amplifier, you really only want it to operate on the differential voltage and ignore or reject the common mode. So we can see that there's a common mode change with the common mode input change. But let's take a look at how the gain changes under those conditions as well. So to do that, let's put on a fixed input voltage difference. Now let's see, with a 3 volt common mode, and let's see if I get to some value here, say a 25 millivolt input difference, I've got a 2.2 volt change. So let's keep those measurements in mind. A negative 25 millivolt input difference, a plus 2.2 volt output voltage difference with a 3 volt common mode. So here now I've adjusted the common mode voltage from 3 volts down to about 2.496 volts with that same negative 25 millivolt input difference. Instead of having 2.2 volts of difference at the output, and now I'm seeing just 1.7. So our differential gain has changed a lot because as I brought the common mode voltage down, the tail current went down, the collector currents went down, GM went down, and therefore the differential gain went down. And this is kind of an undesirable behavior. So how do we fix this? Okay, so one way to fix that behavior and get rid of the common mode problem is to introduce our friend the current source, which I talked about in the previous set of videos. So instead of having the tail current be determined just by a resistor and therefore the common mode voltage, let's replace that with a current source. So now with the current source with its very high output impedance, we'll create a constant tail current that is going to be effectively independent of whatever the emitter voltage is here, and therefore independent of whatever the common mode voltage is at the input. So since the tail current is now essentially independent or not affected by the common mode, therefore the current through the transistors is not affected by the common mode voltage, and therefore the GM and the gain is not going to be affected by it. So therefore as the common mode voltage moves up or down at the inputs, the voltage drop across the output loads is not going to change because the tail current isn't changing. Therefore the gain is not going to change either. So our differential gain is not affected by a common mode as well as the single-ended gain. So let's go take a look at that. Okay, so I still have a simple current source set up here as I showed in the schematic from the previous set of videos. So what I'll do is I'm going to remove my little 2.2K tail resistor and take the output of my current source and tie that into the coupled emitters here to bias up the circuit. Alright, so let's start off with the input voltage disconnected here. So I've got about that 2 millivolt offset that I was seeing at the input before, about a plus 130 or so millivolt output voltage difference. Here's my common mode voltage at about 2.5. The collector of transistor number 1, Q1, is sitting at 6.37. If I reach over here and change the common mode voltage, watch what happens to the difference voltage and my output voltage here. So let's go up to, so I'm even at 3.26 volts. My collector voltage didn't change. Let's go back down, 2.77, 2.5 or so. If I keep going down, 1.9. My collector voltage is not changing at all. Okay, my output voltage difference is not changing at all. So now even with large changes in input common mode, the common mode and the collector voltage is not changing at all on our diff pair. So let's make sure that the gain is not changing either. Okay, so here's that same negative 25 millivolts going in, and it's giving me a 2.4, 2.45, 2.46 volt output voltage difference. Now it's not the same as what we had with the tail resistor in there because the current isn't the same. But the idea is that this set of voltages here, a negative 25 millivolt input and a about 2.46 volt at the output, should be consistent regardless of where I set common mode. Okay, so I've moved the common mode voltage down to 2 volts, and I'm just dialing in that minus 25 millivolt input difference here, and let's see if I can get close in there, right about there. So I can see that even with a 1 volt change in the common mode, I'm pretty close to that minus 26 millivolt input difference, and I'm sitting in that 2.48 output voltage difference. You know, a slight change, but not nearly as much as we saw with the tail resistor as opposed to a current source for that tail current. Yeah, so the addition of a current source to create the tail current has really improved the common mode rejection ratio of this amplifier by making the performance of the amplifier basically independent of the common mode input voltage. So that's a good thing. Now, if you think about it, we're actually getting pretty close to making something that looks like an op-amp, right? Because ideally an op-amp is going to have high gain. It's only going to respond to the voltage difference at the inputs, okay, and not to the common mode voltage at the inputs. So we've kind of solved, or at least addressed that to the first order in terms of input common mode. Now the only other thing we need to do to make it closer to an op-amp is to make the gain much higher. We're talking about a differential gain here that's on the order of about 100 or so. We need it to be closer to, you know, maybe 100,000 in order to make, you know, the basics of an op-amp. And there's a way to do that as well. Of course, one way to increase the gain of this circuit dramatically is to replace the load resistors with a current mirror. And we covered this in the previous set of videos as well. So now what happens, let's consider the case when the input voltages are equal. The tail current splits equally between the two transistors. So therefore I've got half the tail current flowing here, half the tail current flowing here. Now if these two transistors are perfectly matched, then as we covered in the current mirror, this collector current is going to equal that. Everything is going to be equal, and then our output voltage is going to be sitting halfway between, you know, essentially these two emitter voltages. But what will happen now as you start to have a small voltage change one way or the other, if this current goes up, this is going to try to push more current in, this is going to accept less current, okay, and the voltage is going to rise. Same thing, or the opposite happens if the voltage goes the other way. And since this has such a high output impedance, the GM times the load is much, much higher, and we'll get a very, very high gain. Now what we've sacrificed is now it's a single-ended output instead of a differential output, but the gain is much higher. This is starting to look like the very, very rudimentary beginnings of an op-amp. Okay, so I've got this set up here now. I connected up the output of my differential amplifier to my little current mirror that I had here from the previous set of videos. And we're still looking at the output voltage difference between the two collectors. Okay, the collector that you know, of C1 is sitting just about a dial drop below the power supply here. And still looking at that little bit of input voltage difference. I've got the common mode still set to 2 volts. But remember when we first started off, I put my finger on one of the transistors to change its temperature, and we saw a few hundred millivolt change at the input difference. Let's look at the same thing now. I put my finger on one of the transistors, and we're very quickly ramping up to, you know, several volts of difference now, just with that small temperature change we're getting from my finger. I go to the other transistor, we could bring it back the other way. So we can see the gain is actually much, much higher now. In fact, I was trying to, you know, apply my voltage here and adjust the input voltage difference to try to get the voltage to sit mid-rail, and I just couldn't do it. I just can't, the gain is so high that just a few millivolts one way or the other kind of rails the voltage difference one way or the other. And this is, you know, kind of like the open loop behavior of an op-amp. You know, without feedback, you're not going to make the output do anything usable. And that would be the same thing in this case here. So take a look at this circuit structure, with the current source here, current source here using mirrors as the load. It's called an active load. And start looking through the data sheets of the op amps you like using, and you'll start to see these structures kind of built in there. You maybe start to recognize why some of these structures are used and how they form the basics of how the op amp works. So anyway, I hope you enjoyed this video, learned a little bit about the diff amp, or emitter coupled pair, or long-tailed pair as it's also known, and what its basic characteristics are, what some of the failings are in terms of common mode gain and common mode rejection, how current sources can help improve that behavior, and basically give you sort of the building blocks for building things like op amps and other more sophisticated analog circuits. Thanks again for watching. Comments are always welcome, and if you like what you see, please subscribe. Give me thumbs up and things like that. That all helps keep me motivated to do more of this. Thanks again for watching.